Welcome back to Thermo Shorts, where we're going to give an overview of the material that will be covered on the second exam. Essentially, this exam is about open systems, but we've also learned about the second law and entropy. We know about heat engines, heat pumps, and refrigerators, and how to characterize them. We learned about isentropic efficiency, and we learned about Rankine cycles. Generally, we have this 4-step process for solving open system problems. After we draw our control volume, we do conservation of mass, where we can make some assumptions. Notice these are common assumptions and not assumptions you will make every time. Then we will do conservation of energy, or the first law of thermodynamics. We need to remember that the units in the kinetic and the potential energy terms are always a pain, especially when we're dealing with imperial units. So we need to check our units in these terms. And we have a series of assumptions that we might be able to make for this expression too. Remember, in all of these cases, I will encourage you to start with the first law, clearly state your assumptions, and cross off terms that go to zero as you make those assumptions. In this expression, we need to know how to find the change in specific entropy. And when it comes to this point, we have to ask ourselves, what's the fluid? And depending on the answer we get, there are different methods we can use to find delta H. We talked about ideal and real pumps. Now, ideal and real pumps, if we make a specific set of assumptions, the ideal pump will often be isentropic, just like the ideal turbine. And that's why we started to draw TS diagrams, so that when we see a vertical line for a pump or a turbine, we know it's probably ideal as well. The real pump will see an increase in specific entropy, just like the real turbine. So in order to compare the real and ideal pumps and turbines, we need to know something about isentropic efficiency, which means we need to remember which one of the powers is larger for each of these cases, the ideal power or the real power. We also talked about the second law. So we can talk about the second law as a rate equation, but also as a concept. And Kelvin and Planck told us that in order to run a heat engine continuously as a cycle, we need to be able to communicate with some cold reservoir. Then the input heat that we put in has two paths that it can take, one as work produced and the other as heat rejected from the engine. Clausius told us that we can make a machine that removes heat from a cold reservoir and dumps heat into a hot reservoir. But in order to do that, we have to put work into the system. Remember, we need to plug our refrigerators into the wall. We can also talk about the second law as a rate equation, which I'm showing here. Some common assumptions we can make include that the system is at steady state. Maybe it's one inlet, one outlet. And if I can, I'll try to draw my control volume so this expression is adiabatic, because this is the term that most people make mistakes on, because we have to take the temperature outside of our control volume, the thing we're transferring heat to, and we have to put that as an absolute temperature in Kelvin or Rankine. In order to solve this second law equation, we need to be able to find our change in entropy, which again is going to depend on what our fluid is. And we have different expressions for different cases as shown here. Delta H for ideal pumps is another thing that people tend to make mistakes about. So here we can see that if we make some assumptions about what's going on across this ideal pump, we'll get that the power consumed by the pump is the mass flow rate times the specific volume times the pressure difference across the pump. Remember, if we use the sign convention that we normally adopt in thermodynamics work into the system is negative. So the pump power will be negative. We'll also have to think about how to deal with ideal compressors or ideal turbines when the working fluid is air. And sometimes when we do that, we'll have to assume that the specific heats are constant. When we do that, we can use these expressions for delta S, but when delta S is 0, we get the expressions shown down here for isentropic processes. If we have variable specific heat and delta S is 0, we'll want to go to table A22 and look at reduced pressures and reduced specific volumes. If I know the pressure ratios, then the pressure ratio is equal to the reduced pressure ratio, and the specific volume ratio is also equal to the specific volume ratio if my process is isentropic. So these are expressions that I can use in that case if I have variable specific heat. And this image here is taken from the equation sheet we've prepared for this class. So these ratios are very important if you have variable specific heat, ideal gases across isentropic processes. We'll use these expressions at the bottom if we have constant specific heat for these same isentropic processes. We learned about system integration, putting different components together to make cool things like heat engines. And I have this general process which ultimately means how do we answer these three questions? How do we characterize the system? Is the system open or closed? And what's the fluid? It doesn't matter if we're talking about a heat engine or a thermal management device, we always characterize these things as the desired energy effect divided by the energy cost. We have different equations for different cases. Remember, if it's an ideal or Carnot device, then we can replace ratios of heat transfers with ratios of temperatures, being careful to notice the temperatures that stand alone have to be absolute temperatures. Finally, we talked about Rankine cycles. So a Rankine cycle is a heat engine that's made up of at least these four components here. If I draw a TS diagram, it would look something like this, where we're moving back and forth between a high pressure and low pressure state, and we're bouncing back and forth across the vapor dome. It's a heat engine, so this is how I characterize the engine for the real and the ideal case. I can also talk about the backwork ratio, recognizing that the power plant is the first consumer of the power plant. As I move through the system, I can look at each component and make a series of assumptions. Again, just because these are common assumptions doesn't mean I'll make these assumptions every time. But these are the expressions that I would generally expect for these Rankine cycles. Now remember, you might get a wrinkle on an exam that deviates from these expected equations. So that's it for this episode of Thermo Shorts. Good luck on your second midterm.